look at these carts right here. Okay, so here we have some carts. And we're going to look at this cart right here, the one on the left. Okay, so looking at the cart on the left. Okay, it's a really cool set of carts. If you push this little button right here. Oh, look at that. All right. So the question is did the cart on the left change its momentum? Okay, let's watch again. So now that you know what you're watching for, you got the cart on the left. Did the cart on the left change its momentum? But yes, why? Okay, because it's moving. So after I pushed the button, it was moving, and before I pushed the button, it wasn't. And so because it changed its velocity, First Hour had an interesting perspective. They said that they're just going to watch from now to now. If that's the case, would the cart changing its momentum? Why not? It wasn't changing its velocity. So that's a really interesting perspective that I hadn't thought about before, is depending on where you're looking, it may or may not be changing its momentum. So if you're looking from now to now, it's changing its momentum. Okay, because it went from not moving to moving. But if you're looking at the cart from now to now, it's not changing its momentum. This is not changing its speed. That's really interesting. So it depends on when you're looking as far as is there a change in momentum. All right, so what we're going to do today is we're going to shift our perspective even more. All right, so now what we're going to do is we're going to look at both cars. So instead of just looking at one car like we've been doing all the way up until now, we're going to take a look at both cars. Okay, so I'm going to hit this little trigger thing, and we're going to see what happens. Okay, that was pretty cool. All right, so what happened? Okay, that guy changed its momentum. And this car here. What happened here? It changed its momentum too. So when this car changed its momentum, what we see is if we're looking at both cars, the other car changes its momentum too. Now, momentum is an interesting quantity because it's a vector quantity. So when we look at the change in momentum of the car on the left, what do we notice about it compared to the momentum of the car on the right? They both change their momentum in terms of vectors. One's negative and one's positive. One's going to the left and one's going to the right. So what's going to happen with these two changes if one's going to the left and the other one's going to the right? Okay, what? They might cancel out. They might equal 0. All right, so this leads us to a really interesting principle, and it is the conservation of momentum, where we start out with no momentum, and we end up with no momentum. Why? Because the momentum of the cart going to the left is going to cancel out the momentum of the cart going to the right. All right, so what's the difference? Why in one case did we change momentum, and in the other case we didn't? The question is where are the forces? In the first situation, when we see the change in momentum, okay, what we have is we have an external force. Okay, here I am on the outside, pushing that thing forward, and all you're focused on is this car over here. Okay, so if we have an external force, we can change momentum. But if we take our picture and we expand our picture so we see both cars, so the force is inside, the force is in between the two objects that we're looking at, now our picture is bigger and we see that momentum is conserved. So if our forces are internal, so that's when momentum is conserved. All right, so when is momentum conserved? When the forces are internal. Okay, so what does that mean? That also means when there is no outside force. So if I'm not on the outside pushing this forward to make it speed up, or if I'm not on the outside, like yesterday's lab, slowing it down, if I'm not on the outside, if I'm not an outside force, then our total momentum will stay the same. The momentum of one object increasing will be the same as the other object. So if we look at yesterday's lab and we include the barrier as part of our picture, then the force would be internal. And the momentum of the car before would be the same as the momentum of the car and the wall after. So if we make our picture bigger to include the forces, then we have this conservation of momentum, where the total momentum before is equal to the total momentum after. Cool? All right, so let's take a look at an example. All right, so what the heck is going on there? Explain. Are the forces external or the forces internal? Okay, we can look at it both ways. If the force is external, there was a force acting on the guy, pushing him backward, causing him to have a change in momentum. Okay, that's what we were looking at all last week and yesterday too. But if we think of this as forces being internal, so we have the guy and the gun, and we have an explosion inside the gun causing this to happen, we think of the forces internal. Then what we have is we have the sum of the forces to start out with is equal to the sum of, the sum of the momentums to start out with is equal to the sum of the momentums to end with. We have to decide, let's start. When do we look at this picture? When do we want to call this a start? Maybe before the forces act? That's the usual place to look. What was our momentum of our guy and his gun and the bullets before the start? It was 0. So we start out with no momentum. And at the end, we have our guy and his gun and our bullet. Okay, what happens to the bullet? Yeah, the bullet, if we look at the bullet, the bullet is going this way. All right, so the bullet's going that way. And so when we want to call the momentum of the bullet going to the right, we'll have to say the bullet has a positive momentum. So if the bullet has positive momentum, how do we get back to 0? Yeah, we give the guy in the gun negative momentum. All right, that cancels out. We get 0, and everything is good to go. So if we see momentum going one direction, if there are internal forces, that means that there's got to be momentum going the other direction too. Cool. All right, so same thing happens to rednecks. So here we have the redneck version. All right, so. All right, so same thing happens to rednecks too. So if we don't know about the conservation of momentum, we're not watching for that momentum going the other direction. We expect to see our bullets going, this way, and that's it. But we now think about the internal forces. If we have internal forces, if we have momentum going to the right, what has to happen? If we have momentum going to the right, we have to have momentum going to the left to cancel that out in our explosion here. All right, so what we're going to do is we're going to see if we can actually use this to solve a problem. Like, for example, in this case, what we have is we have this, this guy, or we'll just say we have a gun and we have a bullet. Okay, so that's our system. And to start out, what is the momentum of the gun and bullet? 0. So before the forces is usually when we start looking at these problems, the momentum of the gun is 0 because it's not going anywhere. The momentum of the bullet is 0 because it's not going anywhere. So this is our before, and then we're going to look at our after. So same things, gun and bullet. All right, so we got more information about our bullet. So let's start with that. Okay, so this right here is the sum of the momentums before is equal to the sum of the momentums after. All right, so we got no momentum before after, we're looking at what kind of things together to make momentum. We're looking at what two things? Yeah, so we'll say the gun is positive, okay. But what two things? What two things go into making momentum? What? Velocity is one of them, and mass is the other. So we'll look at the mass of the gun and the velocity of the gun, and then we'll look at the mass of the bullet and velocity of the bullet. So those two things go into making our momentum. All right, so let's fill us in with numbers. Mass of the gun, it says 5 kilograms. Velocity doesn't quite say. Mass of the bullet says is 0.05. And then they give us a speed of 120. All right, so we can do a little bit of algebra and see what happens. All right, so moving this to the left side of the equation. Dividing both sides by 5. When you do that, v comes out to be negative 1.2 meters per second. So what's up with this negative thing? That means that the gun gets pushed backwards. All right, so the gun ends up going backward. That's what that negative means. That is something that doesn't look too safe, does it? That gun going flying off behind it. Yeah.
So anytime
in the case of these stationary explosions, which is how, like bomb technicians, know they're missing fragments. So they look at the fragments over here and they're like, oh, they don't cancel out. Here, that I probably ought to go fine. All right, so in the case of these explosions, the momentum going one way has to cancel out the momentum going the other way because they start at 0. But do all of these problems start with 0? At the end of the day, we're going to take a look at a couple that don't. All right, but yes, in the case of an explosion, if we have stuff going one way, we'll have stuff going the other way. All right, so in this case right here, we got to the bullet going one way, and that means the gun's going the other way, and that could knock somebody's eye out if you watch the Christmas Story. Okay, so that's how you shoot your eye out. All right, so what we want to do is we want to talk about ways to make, what is his name, Frankie, Georgie, Ralphie, that's it. We want to see how we can have Ralphie be safer. All right, so let's take a look at this equation right here and see if we can come up with ways for Ralphie to be safer. Okay, so in other words, we don't want the gun to shoot his eye out. Okay, so we want to make this smaller. So what kind of things can we do about the bullet so that the velocity of the gun is not going to be so bad? What? Make the bullet smaller. So instead of using a 44, maybe you'll use a 22. Right? So make the bullet smaller. So if the mass of the bullet is smaller, okay, that means this number is smaller. If this number is smaller, that means that the speed that the gun is getting thrown back is going to be smaller. So making the mass of the bullet smaller is better. So if you are not used to shooting guns, using smaller bullets is easier. All right, what's another thing that we can do? So we can change the mass of the bullet, change the velocity. So Ralphie's mom probably doesn't want it to shoot bullets quite as fast. So we make the velocity of the bullets coming out of the gun smaller, then Ralphie's going to be safer too. All right, so what can we do about the gun? We can make the gun bigger. So if you go to a gun shop and you're like, oh, I'm a little gal, and I want the smallest gun possible, okay, is that the safest gun for you? No. Okay, by having a small gun, that's going to have a big recoil velocity. So actually using a heavier gun, okay, if this number is bigger, you're going to have a smaller recoil velocity. So actually having a heavy gun makes it recoil less. Or in the case of a rifle, what do you do with a rifle to make it recoil less? Okay, what did the guy in the previous picture forget to do with his rifle? Put it up to his shoulder. Okay, so if you put the rifle up to your shoulder, what you do is you put your mass behind the gun. So now instead of having just the gun's mass, okay, you have your mass and the gun, and that is going to change the velocity considerably. And that's one of your homework problems, is to take a look at a girl who holds the gun off to the side like this, and the girl who has the gun in front of her shoulder and seeing the difference in kickback velocity. It's quite extreme. Any questions so far? This right here is a pretty deep problem. Any questions on analyzing that? That's pretty straightforward. Okay, awesome. All right, so these explosions. They're not rocket science, or are they? Well, let's take a look at this. If we got a nice rocket right here, and we want it to have a velocity going here, what do we have to do? Stay on the ground. Okay, we could apply force. So that's our what we did in our previous chapters. We could apply a force so that we get a change in momentum. All right, but if we want our picture to have internal forces, so we got the explosion of the field, internal forces, now our momentum before is equal to our momentum after. So if we had no momentum before, but now we want momentum going forward, what do we have to do in order to get that? We have to have a change in velocity. So a force is going to cause this mass time change in velocity. But what do we have to have down here? Yeah, we have to have a negative momentum. Right? So these right here will cancel out. This one going forward, this one going backward, and our rocket can take off. Or getting a little bit down to Earth. New Christmas wish list.
Swimming with dolphins. For many will be a dream come true. Obviously, you'll be splashing around while the dolphins glide through the water. Unless you've got one of these. A flyboard. No, it's not clever special effects. It's real. Actually, it's amazing. Creation of French jet skier Frankie Zapata. Half a water jet turning into some kind of amphibious jetman. Frankie takes it through its paces in his native Marseille. He says he can climb more than 30 feet above the sea. He can do somersaults. Obviously, as Frankie's been jet skiing since he's 17, he's pretty good at this. And it might take customers just a little while before they get the hang of it. Swimming with dolphins, priceless. Swimming like a dolphin, around €4,900 to you, or just under £4,200, which actually sounds quite reasonable. Not sure you can use delivery. So if you haven't made that Christmas list yet, and you've been really, really good, then you can have hope.
How does it work? Yep, so we got water with mass going this way, and keep them in place so that our momentum is 0. What's going to happen? Yep, so the water goes this way, and then his mass has a velocity going this way. All right, let's take a look at another example of an explosion. Okay, this one here, it's just a 2-object explosion. Occurs quite often around here. We got a nice little tourist, okay, in a canoe. So there's our canoe. He's pulling into Heaveners. There he is, right there. 65 kilograms, and he's in this nice 50-kilogram canoe. All right, so there we are. Pull into the dock. And he decides he's going to make a leap for it. Okay, so he's going to jump onto the dock. All right, now the question is, all of you had experience with Heaveners, what's going to happen? Okay, he's going to face plant. Why? Yeah, the boat is not going to just stay there. The boat is going to go backward. Okay, so if he's going this way, the boat's going the other way. Okay, so we have an explosion, another explosion right here. So what we're going to do is we're going to try to analyze it very similarly to the gun and the bullet. All right, so when we do this, internal forces or external forces? Are forces inside the system or are they outside? Okay, so he's pushing this way, the boat's getting pushed that way. Are forces in between the objects that we're looking at, or are the forces acting on our object from outside? Okay, we could look at it like we have been for the last couple of days, where we have a force causing our dude to change his momentum. But we want to know about the boat. So if we want to know about the boat and the guy, now the forces are inside, between the boat and the guy. And that leads us to our sum momentum 4. This is sum momentum after. Yeah.
So you say that when you say outside forces, that's just one force.
Yeah, so if I was just going to take a look at the guy and all of a sudden he was going to speed up, the boat involved, that would be an outside force causing him to change his momentum. But the only reason why he can go forward is because the boat is going backward. Now the forces are inside because we're considering both objects. All right, so if it's just the dude, external forces. If it's the dude and the boat, then the forces are internal. All right, so here we have just the dude, and we have the boat and the dude, and now we have internal forces. So that means the sum of the momentums to start with is equal to the sum of the momentums to end. That's how we choose our equation. Had we just been looking at the dude and not the boat, then what we would have used is force times time is equal to our change in momentum. Well, if we were just looking at the dude, this is the equation. If we're looking at the dude and the boat, this is our equation. Okay, so that's the difference. Yesterday, we were just looking at the car and our crash. Today, we're looking at the car and the box. All right, so here we're looking at the dude and his boat. The forces are internal. So that means we want to use this equation. What's our starting momentum? Before the forces is usually when we think about it.
Yeah.
0. Our starting momentum is 0. And after we have our boy and we have his boat. All right, so we have those two objects. And the momentum of the boy is 65, and his speed, it says, is 4, thank you. And the boat, it says, is 50, and its speed is, we don't know yet. But after a little bit of calculation, 65 times 4, go that to the left side of the equation, divide by 50. Our V turns out to be negative 5.2 meters per second. And what's up with this negative? Yeah, so if we say the boy is positive for its velocity, this negative means that he's going backward. The boat is going backward, the opposite direction of the boy's velocity. The momentum of the boat is the opposite direction of the boy's momentum. Cool. All right, so we go down to Florida, and we have a nice raft down there. Maybe it's afternoon, but we go somewhere nice and warm. Talking about warm again, and we have this nice little raft. And here's Joe, and he's 80 kilograms. And here's Jane, and she is 50 kilograms. And along comes a killer bee. So there's our killer bee. And when the bee comes, Joe and Jane are going to make a jump for it. Okay, Joe is going to jump to the left with a speed of 6 meters per second, and Jane is going to jump to the right with a speed of 8 meters per second. And the question is what is the raft going to do? It's going to maybe fly straight up. Okay, so maybe the raft is going to fly straight up. Okay, so it might bounce, but is it going to have a left or right direction to it? Okay, so we want to analyze left or right. Who is going to get hit in the back of the head, Joe or Jane? Okay, we can do a little bit of math to find out, right? Okay, so Joe might get hit in the head, Jane might get hit in the head. We don't really know until we do some math. All right, so external forces or internal forces here? Internal forces. Okay, so all the jumping happens between the people in the raft, and the raft is part of our picture. So all of the forces are internal. That means that we're going to use the sum of the momentums to start with is equal to the sum of the momentums after. And what's the sum of the momentums before? Okay, we're getting the hang of this. When we have these nice explosions, and the sum of the momentums before is 0. And then we got to Joe, and we got Jane, and then we got the raft. And we can figure out what the heck is going to happen with the raft. Okay, so Joe is 80 and his speed is 6. Jane is 50 and her speed is 8. And the raft is 40 and the speed is, what's wrong with this picture? Guess what's wrong with this picture? Okay, so they're both the same. Okay, so we see these guys jumping in different directions, and are we indicating that in our momentum? No, we probably ought to do that. So who do you want to be positive, Joe or Jane? Okay, Jane, I saw positive. Okay, the big tails make her positive. So Jane's going to be positive and Joe's going to be negative. All right, so what we're going to do to make this a better picture is we're going to put a negative for Joe and a positive for Jane. All right, now we got the right picture. Yeah. Oh, yeah, that's too. Thank you. Yeah, got to get the momentum equation. All right, so now we're ready to solve. All right, so let's go and put our numbers together. We got 80 times -6 plus 50 times -8. Oh, okay, try again. Buttons just work on the calculator. All right. So when we do our math, I push these over to the other side of the equation. What we get is 80 is equal to 40 times v. I do a little bit of more math. Q is equal to v. What does that mean? Let's throw some units on, meters per second. All right, so we got, and what is that? It's going in Jane's direction. So we notice positive, Okay, this is going in Jane's direction. So Jane is the one who has to watch out for the raft coming up and whacking her in the head. Joe is perfectly safe according to calculation. All right, so cool things that physics lets you know is who's going to get whacked in the head. Life-changing consequences there. All right, so next thing we're going to look at is the starting momentum always going to be 0? Probably not. Otherwise, I wouldn't have asked you that question. So the starting momentum may be 0, and sometimes it's not. And in the case of collisions, when things are running into each other, they oftentimes start with some momentum. Like, for example, these two balls right here, we're going to have them run into the table. Okay, they start with some momentum. Okay, they were moving, and this one stopped and this one bounced. All right, so but they start with some momentum when they have that collision. And so we'll have a starting momentum, and then we'll analyze what happens at the ending momentum. And in one case, it stops, and in the other case, it bounces back. And so we have two different things we're going to look at. And today, we're going to start with the inelastic one. We're going to start by looking at the one that stopped. Okay, that's inelastic, where things collide, and then they stick. All right, so in real life, what does that look like? All right, that's an inelastic collision. All right, so other examples of inelastic collisions. Okay, that's an inelastic collision. And in fact, that right there is just like our explosion run in reverse. So we ran this in reverse and just looked like the carts right here that started at rest and going apart. So inelastic collisions can look like explosions in reverse. And here's another example of an inelastic collision. Okay, so you after you eat lunch, that's an inelastic collision. Okay, when your lunch eats you, that's also an inelastic collision. So what's up with inelastic collision? what's up with inelastic collisions is usually we start with some objects. Okay, so we might start with 2 or more objects, and they'll start with some momentum. And after, we have those 2 objects that either have the same momentum. That's one way to look at it, 2 different objects that happen to have the same momentum. Or the other way to look at it is we have a combined mass of humanity or a combined mass of terrain that has its own speed. So what is it? Are the forces external or are the forces internal when we're looking at all of these problems? Internal. So we're going to use the sum of the momentums before is equal to the sum of the momentums after equation. Where before we have 2 or more objects. And to make momentum, look at our mass and our velocity. Right after. When we look at these things after, we have 2 objects that happen to have the same speed. That's one perspective. Or another perspective is we have one object that is the same as the 2 masses combined and its speed. And this right here, you'll notice, is what we'll end up with when we do a little bit of algebra on our 2 objects that happen to have the same speed. Okay, so we go from having 2 objects with their own momentums to having one object with combined mass traveling at some speed. But the idea is that our momentum before is still the same as our momentum after. So let's try this with these 2 football players. All right, so what we have is we have this dude, and it says that his mass is 80 kilograms, and he's moving at 4.1 meters per second. So 80 and 4.1. And then we have our other dude that is 85 kilograms. And is he traveling in the same direction or the opposite direction? Okay, yeah, they're both traveling in the same direction. So we'll have another positive, so 5.5. And what we want to do is we want to see what's going to happen at the end. Okay, so people who've had experience with tackles like this, what's going to happen to our slow dude? Okay, so tackles like this. Here we have our slow dude. What's going to happen to our slow dude when he's tackled by the fast dude? He's going to get hit. What's going to happen to him when he gets hit? He's going to fall down. But is he going to slow down or speed up? He's going to speed up some. What's going to happen to the fast dude when he hits the slow dude?
Slow down.
He's going to slow down. All right, so what we're going to do is we're going to do some math and see if what we believe comes true. So when these guys end up tackling each other, they're one combined mass of humanity. Okay, the combined mass of humanity has a total mass of 165. We're just not quite sure about the speed until we put it into our calculator. Okay, so 80 times 4.1 plus 85 times 5.5. And divide that by 165. And we find out that our speed after a tackle is 4.8 meters per second. Okay, so the slow dude was going 4.1 meters per second. Now he's going 4.8 meters per second. What happened to him? Got up. The fast dude was going 5.5 meters per second. Now he's going 4.8 meters per second. What happened to him? Slow down. So physics proves what you said, but now we have some numbers to go with it. The slow guy sped up, and the fast guy slowed down. And these ran into each other and stuck. Any questions? Yeah. Isn't it 5? Basically, this is our conservation momentum equation, and then either set it equal to the 2 objects that happen to have the same speed, or what I like doing is saying there's one massive object, the mass of which is the 2 things put together, and it's got its own speed. Yeah.
Did you do this the same way as the 2 football players?
Yep, so you do the same thing, but if they were running at each other, what would you do to... Yeah, exactly. So if they were running at each other and stuck, then that's actually your homework problem. then you just make the guy who's running the other direction negative. And then you can see if they're going in this direction, they fall backwards, or if they go in this guy's direction, then they still push forward. And that's actually what you're trying to figure out. Is they're right at the goal line, and do they make a touchdown? Do they still go forward and make it across the goal line, or does this guy push him backward and let's stop? All right, so here's another example. What we have is a car running down a railroad track, and a brick runs into it. Momentum is a vector quantity, so we have to consider direction. In this case, what we have is we got horizontal motion and we got vertical motion. But do we care about both of them? No. So the problem, we notice there's horizontal motion and vertical motion, but we don't care. All we care about is what's going on horizontally. Okay, so what is going on horizontally? Do we have external forces or internal forces? When we're looking at the brick and the car, are the forces in the collision outside or inside? Inside. So that means that we're going to use the sum of the momentums before is equal to the sum of the momentums after. Okay, so before we have the car and the brick. At the end, we have the car and the brick together. All right, so taking a look at the car. Okay, looking at the car before, okay, what kind of momentum does it have? Car before, okay, so it's got a speed of 50 centimeters per second. Okay, that's the speed. What do we have to do to it to make it a momentum so that this equation works? What do I have to do this speed? Okay, I can turn it into meters per second. But what's more important to do with a velocity or speed to turn it into a momentum so that this works? Multiply by mass. It's going to multiply by mass. And just to be lazy, I'm going to leave it like this and we'll see what happens. Okay, what about the brick? Okay, we look at the brick and we see it moving vertically. Do we care about vertical right now? No. So what's its horizontal motion to start out with? 0. All right, so now we got the car and brick smash up. All right, so the bar and brick together, they weigh a total of 5 kilograms. And you want to know what happens to the speed. Okay, does it speed up, slow down, or stay at the same speed when this thing runs into it? So when this brick runs into the cars, will that cause the car to speed up, slow down, or stay the same speed? All right, so doing our math, we find out that 3 times 50 divided by 5 gives us a speed of 30. And what are our units going to be? Our units will be centimeters per second. So with momentum, you can get away with not changing units. You just have to be careful and carry your units through if that's your prerogative. So what happened to our car? Okay, it was going 50 centimeters per second before the brick landed in. And after the brick landed in, just like we calculated, it's going 30 centimeters per second. It didn't slow down. So when the brick came into the car's going to slow down. So this is something that railroad car operators have to think about. When they're loading the cars with coal or grain, okay, what's going to happen as that stuff starts filling up the cars? The train is going to go slower unless there is some impulse from the engine to cause it to change. All right, one final problem, and then we'll call it quits for the day. Okay, and this is a problem of the bug in the bus. All right, so to lighten the mood before we do this problem, what is the last thing to go through this bug's mind when it hits the windshield of the bus? Okay, both sides are front. Oh, okay. Okay. Yeah. So okay. So they go this way, but I was thinking the butt because the butt would keep going on. So. All right. So yeah, last thing to go through his mind are bug parts. All right. So here we are. I like your eyes too. All right, so here we are. We got this problem where this bug is going to be flat against the windshield. And what we want to do is we want to figure out what the change in momentum is for the bug and what the change in momentum is for the bus and whether or not they're the same or different. Okay, so going into this, do you predict that the bug will have a bigger change in momentum, or the bug will have a smaller change in momentum, or the bug will have the same change in momentum as the bus? Okay, yeah, predict same, why? All right, so change in momentum is mass times change in speed. So the change in speed for the bug is going to be really big, but its mass is small. All right, the bus, okay, its mass is big, and its change in speed is really small. So that kind of logic does indeed lead you to the change in momentum for both bug and bus being the same. Let's mathematically prove it. Okay, so gut feelings, sometimes they're right, sometimes they're wrong. So what we're going to do is we're going to mathematically prove that these are going to be the same. Okay, so that's going to be bug, bus. But this is the intuitive way of reasoning this out. But what we want to do is we want to reason this out with numbers so I can feel a little bit more confident. All right, so to get the change in momentum, we need a mass and we need a change in velocity. We got a bunch of starting velocities, we don't have any ending velocities. Is it possible for us to get an ending velocity of the bug and the bus after the collision? Flat, yep. So what we have is we got our bus, and we got our bug, and we got our splat. So it is possible for us to figure out the speed of splat after by using our conservation of momentum, where our bus has a mass of 5,000 and a speed of 40 meters per second, and our bug is a little bit lighter, 0.005 kilograms, and the speed of negative 0.5 meters per second. All right, so there's our bug and our bus to start up with. And after, what's the mass of our splat? We got 5,000.005. And with this, we could figure out the missing speed. And the missing speed comes out to be 39.99996 meters per second. All right, so the bus is going 39.99996 meters per second. Okay, did the bus really notice? The bus didn't really notice that it hit a bug. Okay, the bug was going one direction, okay, kind of slowly. But after it hits the windshield, it's going this fast, the other direction. So the bug notice? Yes, so the bug notices. The bus hardly notices that it hit a bug, but the bug definitely notices it hit a bus. Okay, very, very different final speeds. Very, very different changes in speed. Okay, just like Lauren predicted. Okay, very, very different changes in speed. The bus had a small change in speed. The bug had a big change in speed. Okay, so now what we're going to do is we're going to come full circle. Okay, so what we're going to do is we're going to look at the change in momentum of just the bug, and we're going to look at the change in momentum of just the bus. So change in momentum of the bug, and the change in momentum for the bus. Now, we are going to not look at the two together. We're just going to look at the bug, and we're just going to look at the bus, separate. Why would we do that? By taking the two things out of the picture and focusing on one. And now what we can do is we can start seeing the external forces. So we just look at the bus, we can see the external force the bug puts on it. If we just look at the bug, we can see the external force the bus puts on it. That's why we step back and look at just the bug. And that way we can see the external force. And now that force that was between the bug and the bus now is the force on the bus and the force on the bug. All right, so if we're just looking at the bug, what we have is the mass bug and the change in velocity for the bug. All right, so the final velocity of the bug, 39.99996, and then the starting, minus off the starting, negative 0.5. I'm going to put that into our calculator, 0.005 times 39.99996 plus 0.5. That comes out to be 0.2025 kilogram per second. All right, that is the change in momentum for our bug. All right, for the bus. Okay, for the bus, what we have is we got a big mass now. So there's our big mass. And now for the little change in speed. We find out by doing math that Lauren's intuition was right. When we have a little mass with a big change in velocity, what we get is the same number as a big mass with a little change in velocity. But there is one difference. What is the difference? The negative. This is interesting. The change in momentum of the bug is going one way. The change in momentum for the bus is going the other. It's equal and opposite. Oh, I've heard that before. Where did I hear that before? Newton's laws, Newton's third law, said we had equal and opposite forces when we had interactions like this. Taking this full circle, let's take a look at the force. Now that we're looking at changes in momentum, okay, we can take a look at that external force. We have the same change in momentum. Okay, they're in contact for the same amount of time. What's that going to do to our force? Our force is going to be the same. But if one momentum is positive and the other momentum is negative, they're going to be the same size, but opposite direction. Equal and opposite. One way to look at it is in terms of change in momentums. The other way is looking at Newton's third law. The way we look at it now, equal and opposite forces. All right, so that's pretty cool. And that brings us to tomorrow, where we're going to talk about elastic collisions. All right, so a little bit of practice with what we talked about today, and that is our explosions and our inelastic collisions, where you get to find out what happens when people jump off of rafts, when we have linebackers tackling, and whether or not they make touchdowns. Yeah. The answers to these will be under the classroom, so you can check.